start so we can finish.
Okay, so welcome to Lesson 6, Resolution of Vectors. Same questions as you've seen before, so there's nothing necessarily inherently different. We're still creating diagrams, which means I'm still setting everything up in the same way. So let's read through the first question. You have, it says the Hulk is pulling his daughter on a sled. Right? So the first thing that you would definitely want to do is you want to make sure that you create a diagram. So if here is my Hulk on the sled. So you can draw a beautiful sled like that. It doesn't matter. Here's a person on it. But essentially, this is the Hulk, and he's pulling on the sled. Okay, generally, I kind of make the arrows going up to the person's face, even though it's obviously not where they're pulling from. But it doesn't matter, right, when creating those diagrams, which one you use. So from this, I have a tension, and let's just say rope, because there's no road. The tension in the rope is 25 newtons. Okay? So if you're going to your diagram, this is going to be so interesting today. Here, this is a 25 Newton force. Notice he's pulling the rope towards him, and that's the tension in the rope, not the road. And it says it's making an angle of 36 degrees to the horizontal. Draw a diagram showing the resolution of the forces, so don't freak out about that yet, and determine the magnitude of the horizontal and vertical components. So that's kind of what you get to see here. In terms of finding the different components, this would be my x component, that's my y component, right? And assuming that this person is actually standing up straight, means that I can kind of create, is that unfrozen? Yeah. This would be my fx, like just my x component. And I'll say that's my y component here. Assuming he's straight, it's a right angle triangle. So I can use SOHCAHTOA. So anytime you have kind of a person pulling on a mass, whatever it is, and I just realized our person doesn't have arms, so I just gave him some arms. Okay. So if I were to look for the vertical component, the y component, you're looking at opposite over hypotenuse, you're looking at a variation of sine. So remember, sine of 36 degrees equals opposite over hypotenuse, so I'll just write f of y over 25. And if I were to look at my other ratio, it would be cosine of 36 equals adjacent f of x over 25, and then I can solve for both of those values. When solving for those values, I get the magnitude of f of y, and just writing it out like this, to be 14.3 newtons. And I get the magnitude of my x component.
It's not showing.
Oh, just kidding. It is for me, it's not for you. That's why this is a fun day. F of x being, that would be y, because I have my, people watching this video, if you understood how frustrating this is, 20.5, beautiful. So I don't have a calculator. 20.5 newtons, and we're unfrozen. Beautiful, those are my horizontal and vertical components. So resolving is no different, setting up the diagram is no different, just a little bit different phrasing. All right, let's try another one. This one's kind of like, yeah, that's it. Version 2 of question number 1, but it's harder. Okay, so that was the intro. Here's, pardon?
No right angles.
Well, there is a right angle, but I'm looking for different kinds of tension. So let's look at this. I have a box, and it's resting on a ramp. As soon as you have it, you see a ramp in a question, draw like a little pizza slice. Okay, that's my ramp. It says the ramp, that is, should be inclined, apparently, at an angle of 30 degrees to the horizontal. And I have a box that's sitting on the ramp. Yeah. Okay. So it says, calculate the force of friction that would be required to keep the box from sliding down the ramp. So this means that there is no movement. What do I know about vector diagrams? For there to be no movement, I need what kind of shape? What do I know if I were to make a vector diagram with straight lines? Like this. Like that plus this doesn't, yeah, I need a triangle, right? I need all of my forces in a triangular way. Okay, because I want them to cancel out. I don't want the box to go anywhere. The box is sitting there, so I want all the forces that can be acting on this box to align in a triangular way. So what kind of forces are acting on this box if we were just to talk about it? Yeah, okay, so I have gravity pulling down. What else? Normal force. Okay, so normal force pushing up. And I also have another force, a force of friction. Okay. So how I'm going to illustrate this is in my diagram, and I encourage you to use, it's relative to the plane, right? This is my normal force, F, and I put a little N, force normal.
Isn't gravity though?
Yeah, so that's normal force. Gravity goes right down, F of G, and I have a force of friction. Are we all okay with why my force of friction is going up instead of down? Okay. Yeah, because the friction rate, that's the force that's keeping it there. It's pushing it up because the box would naturally want to slide down. So what I want to do is I want to take all of these forces and arrange them in a way that they are circular. I kind of have that circular movement. So to do that, I generally always start with my F of G force. So F of G goes down. From there, I have my force of friction. And that should add to my F at N. So that's kind of that vector version of that. Now the hardest part is actually figuring out the angles within my diagrams. Easiest thing to start with is here. Force of friction is always relative to the horizontal plane, and this is perpendicular. If that is essentially the new horizontal and that's perpendicular, what's the angle between the F and the N? 90. It will always, always, always be 90. So you can kind of add that into your diagram. So between the friction, and I know you're going to be like, yeah, it's not dry. It will dry. Ah. Adding in that 90 degrees there. All right. Now I need another interior angle. This 30 degrees is relative F of G, so that's 30, and it's relative to this horizontal. Would you agree? So that 30 will be between my F of G and my F of N here. So in my diagram,
How come it's a right angle?
it's a right angle because my F of F, my friction, is parallel to this, so this is a parallel line, and that is a perpendicular line, so that will always be a 90 degree here between the two. Okay. My 30 degrees, if you're looking, notice again for that F of G, the 30 is relative. F of F is the same as my plane, so that angle between this line and F of F, no matter where it is, will be that 30 degrees. So your updated diagram looks like this, right, with 30 degrees there, which automatically means I have a 60. And as soon as you do that, it's not so bad. It wants to know the force of friction required to keep the box from sliding down the ramp. The only thing I have to be careful in this question is I don't know my force of gravity. It says 25 kilograms. You have to convert that into newtons. Do you remember how we do that? Yeah, so multiply by 9.8, but by whatever the number is, so 25. So here, if I have my F of G, is that unfrozen? Yes. F of G is your 25 kilograms multiplied by your 9.8. And I have my solutions. 245, yay! Newtons. So I now have that force. I can kind of draw that in on my diagram. Beautiful. And I know that, again, my F of F is perpendicular to F of N. How can I solve for F of F? Using my new diagram. 90 degree angle. I want to know this one. I know opposite. I want to know adjacent. Hypotenuse is what I know. I want to know adjacent, so I'm going to use cosine. So for my problem, we say the cosine, oh, it's unfrozen. Cosine of 90 is opposite over hypotenuse.
Isn't it kind of like a roll-off use 90?
Yeah, okay, so in terms of using them, there are a few different things that you can use. You can technically use any angle. If I were to use the 60, so let's make it 60 instead. if I look at 60, there. So here from 60 degrees, again, that's my hypotenuse. That's still my adjacent, so adjacent over hypotenuse. So cos of 60 is f of f. I'm on erase mode. F of f all over my f of g, which is 245. And I'll just get my calculator out. I can do a little less moving around. Cos of 60. So I get force of friction is 122.5 newtons. So what's nice is by setting all this up, it's good. Now I have to actually say the directionality of my force of friction.
You just say the what?
The direction. So my force of friction, when we just write a sentence, we say it's 122.5 degrees and it's acting up the ramp. I know it's kind of silly. Therefore, force of friction is 122.5 newtons acting so force of friction is pushing up, right? It's pushing that box up, so the box is kind of able to stay. Okay. Beautiful. Questions on 1 or 2? Seems okay? So box questions are really nice in a test to get. To be honest, you probably wouldn't get just question number 1, maybe if it was just a small component question, but it definitely wouldn't be one of the larger ones. So go look at the next question that you have. In terms of question number 3, it says you have 3 forces acting relative to one another. Right? So there are a few different ways you can look at this. I will always specify in a test situation that my 3 forces, one will be going in a certain direction. You pick a force. If it doesn't specify, and in textbook questions it won't, say I'm going to pick 150 or the 160 or the 170 to go either 100% vertical or totally horizontal. I want one of the components to be 0. Just so that when we all get to this and we get the same solutions, so our diagrams look the same, it makes it easier for me on a test. I'll tell you specifically, do you want, so let's see. I'll go specify which one I want to have a horizontal component of 0 versus a non-horizontal component. Yeah, I'm doing this one first, right? Was that all I have for you guys? Oh, I took some out. Okay, that's sad. Do you have more than that?
Yeah, we go to 6.
Yeah, that's what I thought. 1, 2, 3, 4. Oh yeah, silly. 5, 6. Okay, all right. So let's pick my 3 forces. That was funny. My 3 forces here. For this case, we're going to say that this has a horizontal component of 0. So on a test, I would tell you this. Yep, you can. Please do. Of 0. It would be so much easier if my TV was working. So here's what we do. We create a diagram, and I say this is my 150 Newton force. The reason we make one of the components 0 is it just makes my diagrams really nice. I now have 2 other forces that are pulling on an object. So if this is the object in the middle, my forces go out to the left and the right-hand side. It doesn't matter which way, but you always kind of make it look like a little wheel. Okay. Let's call this my 100 and, again, it doesn't matter which ones you label them. 170 Newton force versus the 160. But again, it doesn't matter. So let's make this here the 170 Newton force, and I'll make this the 160 Newton force. And what angles do I know? They're pulling, at angles equal to each other.
That's all.
At equal angles to each other. Yep, that's all that you know from this component. So the question is asking, find the overall resultant force.
If it's equal angles to each other, can you divide through 60
Okay, instead of doing that, what I would recommend is looking here and saying, let's just divide this. And can we all visualize that that would just be the horizontal, that little purple line? Okay, so if that's that little purple line, remember for my components, so I'll use my f of x components here and my f of y components. For the 150 Newton force, let's just enter that now. What is my x component?
0.
Yeah, there is nothing. Okay, y component, I guess I can put those two together because they're like I have a lot to write. Beautiful. This is going to be 150 newtons, and you have to be specific about the sign. You don't have to say positive, but just realize that you're going to have to say if it is negative. Okay. Again, from there, if I want to know that all these angles are going to be the same, this angle here will be 30 degrees, right? If I take 360 and I'm dividing it into 3 equal segments, I have 120 in each direction. Okay. So from here, I'm going 120, so that gets me to 90, and I go 30 degrees more to get me to 120. Do we all feel okay with that? The idea that this here and this angle there are both 30 degrees if I were to zoom in. Okay. So if I took 360 degrees in a whole circle and I divide it by 3, I say each section will be 120 degrees. So from here to here, that's 120 everywhere. Exactly. And I'm just doing it relative to the 90 so I can just see it a little bit easier. Beautiful. Now that I have that, what is great is that I actually take this and I can see, I'm just going to move my 170 in just to down there so it's out of my way. I can see that I actually have little mini right-hand triangles. Right? Again, moving that 160 just so it's out of my way. It's there. I have these little right-hand triangles, and I can now determine the x and y components of this by using sine or cosine. So from this angle from 30 degrees, if I'm dealing with the 170 Newton force, let's do that one first. 170 newtons, so I want the x component. I'm looking for this one here. That's adjacent over hypotenuse, so cosine. So I'll just do it in pink here. The cosine of 30 is adjacent, so x over 170. Cos of 30 times 170 is 147.2. So 147.2. I need directionality. From the origin, have I gone to the left or to the right for this 170? To the left. Left in x is negative. So make sure that you have that negative value there. Mine kind of looks funny, so I'll redo it. It doesn't look like a negative, it looks like a smudge. Negative. Perfect. Same one I'm going to do to find my y components. Sine of 30. So, oh, not writing. Sine of 30 equals opposite, so y over 170, which is 85. And it is going down, so it's negative. I do the exact same thing for my other components for the 160. So here, remember, cosine, adjacent hypotenuse, so x over 160. And at the same time, I'm just going to set up sine of 30 equals y over 160. And I get x equals 138.6. To the right, so we leave it positive. Sine of 30 times 160 gives me positive 80. But remember, it's going down. Okay. So I have my components for all three vectors. This is the best part. Yay! In a test, my overall resultant is just the sum of all of these vectors put together. So here, if I have the x components, I add them, negative 147.2 plus 138.6, and it says overall, my function is going 8.6 newtons down. Right, that's the x component, so 8.6 part to the left, not down. 150 minus 85 minus 80 means I'm going 15 units down. So those are my horizontal and vertical components of my resultant. To find the overall resultant, the magnitude of the resultant, that's just like my side length. So we use Python. A squared plus B squared equals C squared to finish it off. So here, finishing off my problem for the resultant, the magnitude of R is the square root of negative 8.6 squared plus negative 15 squared. Okay, which gives us 17.29 newtons. Is that right? 8.6 squared, 15 squared, 396 square root, second answer.
Do we have to get
Yep,
the direction?
beautiful. Yes, now here's what's important about the direction. When you report it, you can report it relative, because I don't actually know where any of this is, right? It could be on a different angle. So we report it relative to another force. So my overall resultant is 17.29. If I were to actually just draw it in this picture that I have there, just roughly, so purple, it says it's going 8.6 to the left, and then it's going negative 15 down. So my overall resultant is down here in this quadrant, right? When you report it, you always want to report it relative to another quadrant. So I'll say here, therefore, the resultant is 17 point, I'll just round it to 3 newtons. And I'm going to say it's at, from, FRON, from the 170 Newton force. Okay. Oh, hi, you guys are funny. You're so sweet and kind. Okay. So I've just made my statement there. Please show next time. That I have that reference angle. Here's the reasoning behind it. So in this part, if I were to take this, and I'm going to do this on this, I guess I can't do it on the screen because it's a recording and I want you to be able to see it. Envision this. My resultant is like this. My x is negative 8.6. Is it there? Thank goodness. 8.6 and negative 15, right? It's a right triangle here, and I can solve for that angle theta. So that 13 degrees is this angle in here. So because you're setting up, right? It gives you the relative angle using your SOHCAHTOA. Does that make sense how I would come up with that?
Can you say it one more time?
Yeah. So here, let's try it out. This is my triangle, negative 15. Okay, so if I were to solve for this angle here, I'd say that's opposite adjacent. So tangent of theta is negative 15 divided by negative 8.6. Right? Inverse tan, and it says, okay, this theta is 60 degrees. So if I look here on my picture, if this is 60, right, if this is 60 here using SOHCAHTOA, so saying, well, my resultant is down here. From here to here, it says is 60. Well, if that's 60, that means this angle in between is going to be 30. So that same idea every single time. We're going to try this exact same question with more information, which makes it easier. The more information they give you in these problems, the nicer they actually become. One of these 3 forces questions are guaranteed on your unit test, like guaranteed, and it's guaranteed on your final exam. Okay, so at least you already know one question kind of going into both of those assessments. Okay, let's try it again when they give me more information. So I still have 3 forces acting on an object. The angle between the 100 Newton force and the 120 Newton force is 130, and they give me another angle. What they didn't tell me, find the resultant force. It says relative, 100 Newton force relative to the 140 Newton force. So one thing that you can do to make that easier is to make your 140 Newton force either totally vertical or totally horizontal, making one of the components. I like when it is totally vertical. I think the math is a little bit easier than if you make the horizontal component 0. But again, it really doesn't matter which method you choose for those problems. Okay. So because the 140 is what it wants, this is what I will say, or I'll go to make my picture. And again, that's my screen. So I'll say this is 140 newtons going up. I also have 100 newtons here, and my other force going in this direction is 120 newtons. The angle between 100 and the 120 newton force is saying is 130 degrees. The angle between the 120 newton force and the 140 is 120. Which means that my other force would be 110.
So how do you know which one? Like how?
Which one to put? It doesn't matter.
It doesn't matter.
Generally, when it asks me which one is relative to the 140, I like to put the 140 vertical or horizontal, but it doesn't matter, okay? Because your diagrams will be the same. Every time what you want to do is visualize this as triangles, which means for me, kind of superimposing a horizontal plane. If this is 90, this angle is again 30. That's 110. It means this angle here is a 20 degree angle. And I can now see all of my components. So we're going to write f of x up top here and f of y and realize that we're going to do a tally. Start with 140 newton force, then we'll do 100, and then we'll do the 120 newton force. So my horizontal component for the 140 newton force is 0, and it is 140 newtons upwards. Figuring out my other components, again, visualizing it as a right-hand triangle. If I'm looking at the 100 one, I want the x component adjacent over hypotenuse. So cos of 20, I'll just put this here. Cos of 20 equals x over 100. And please let me know if you have questions while we're going through this. And x is equal to 94. Positive 94. So this is 94. Oh, positive 94, remember I have to take into account the directionality. It's going to the left, x, which is negative. So in my tally I put negative. Finding that horizontal or vertical component, sine of 20 is x over 100. And I get 34. Notice I'm still going down. Negative 34 degrees. The last one I'll do, and I'll just switch colors, is the 120 newton force. If you label them like this, I find your work is a little more maintained. I visualize it as a right-hand triangle. I want the x component adjacent over hypotenuse. Cos of 30 is x over 120. 104 newtons, and that's to the right, so it remains positive, and then sine of 30, x over 120, which gives me 60. Again, going through to tally. We have 10 newtons there. Overall positive 140 minus 34, and I'm at positive 46 newtons. So again, I want to figure out my overall resultant, and it tells me relative to the 140 newton force. So here's my picture. I have a triangle where I'm going 10 newtons to the right, and I'm going 46 newtons up. That's my resultant. That's the R value that I just calculated. Because those are the exact components, if I want that angle, tangent of theta is opposite over adjacent and inverse tan of, so I get 77.7 degrees, which we'll say is approximately 78 degrees. Now that's 78 degrees from here, from the horizontal, right? It's going 78 degrees up. So how far is it relative to the 140? 12, right? 90 minus that 78. So therefore is, we didn't find the magnitude. Let's find the magnitude while we're doing that. So magnitude square root of 10 squared plus 46 squared. I feel like it's a race between me and Graham. Who's going to solve it first? Did you win?
You should get it wrong.
Oh, how about 47?
Oh, yes.
Yeah, there you go. Beautiful.
I just use the different,
Different-
as the vertical one.
Different pictures, that's fine. So again, it doesn't, is that what you mean? Like a
Yeah.
different, yeah. So it doesn't matter how you do that as long as you get your reference angles. So I'll say therefore R is 47 newtons at 12 degrees relative to the 140 Newton force. Are we all okay with why it's 12 and not 78?
Just a quick information question. If we were to do like the magnitude bars and the absolute value thing and the therefore statement, would that be wrong?
No, that's fine. Beautiful. So I really like these questions because they're components. It's the same method over and over. Make my picture, split into components, and do just a ridiculous amount of adding and subtracting. The angle, are you getting a different one? So is your horizontal?
Yeah, I think that's it.
You got the same one? Okay. And again, because it doesn't matter, if your 140 is here, it's still relative to the 140, so it shouldn't matter which way you set up your pictures, which is what's kind of nice about this. Okay, last two questions, and it's kind of nice because we did the hard, not the hard stuff, but long. It's kind of long to do this. Okay, beautiful. When you're ready, and I'll leave that up there for a minute or so while you copy. I'll read the next note because I can see it on my screen. Two kids, is this the right one? I hope so, are playing on a swing. The child is on a swing, and the rope is 1.5 meters long. Okay, so what you want to envision, it says if the total mass of the child in the swing is 20 kilograms, and he's pulled back, so you're envisioning, I think I'm good to go now, but I'm frozen, I see that. You're envisioning that here is my kid, right? He's on a swing. This would be the length of the rope, right? He's attached. So the bottom dot is the person. The top dot is the whatever. If I take this and I pull him back, so that same string length comes back, and it says the total mass of the child is 20 kilograms. So where the kid is here, like in terms of a picture, he has a mass, and he has gravity acting on that mass. Because they're giving you that 20 kilograms, the first thing I will do is figure out my force of gravity. So I get that nice little gravity thing here. What I want to do is envision that as that string goes back, I'm pulling it back at an angle. And it tells me in total he's going back 0.6 meters. So this distance on the bottom is that 0.6, and there's an angle here. So here, that's my distance, that overall distance. Now, tension. There is tension in this rope. It goes this way. I'll write F of T instead of just T. Because I'm pulling the rope. I'm pulling the kid back. There is tension on that rope. Gravitational force. Remember, if he's not going anywhere, find that horizontal force required to hold him in position. Not going anywhere. I'm still thinking about that. You can go. Just give it a good blow.
No, it's okay. It's just that's it.
F of G goes down. I also have another force. What other force is acting on my person? Okay, except in this case it's not a normal force, it's a horizontal force. But it's the same idea, that I have a horizontal force from this person acting at this angle. F of H, it's a horizontal force. So F of G, F of H. And I have my force of tension. So notice I've created that beautiful diagram, and my horizontal force and my gravitational force will be perpendicular to one another. So I automatically now have a beautiful, I'll write that F of G is perpendicular to F of H, which gives me that right-hand triangle. It says find the angle that he is pulled back, or find the horizontal force, sorry. Yep. Is perpendicular. Yep, so that's fancy word for perpendicular. So it means they are at a right angle from each other. And I want to know the overall horizontal force. I know the magnitude of F of G. I don't know theta. What else do I know that I could use to solve this? Why would they tell me that 0.6? So I'm trying to solve for an angle, and I'm not talking magnitude, I'm just talking lengths. I know my distance, if this were just a distance triangle, is 0.6. Do I know the distance of my rope? Yeah, so I actually have 2 steps to do before I can solve anything. The first step is to just envision that this is a triangle, the same right-hand triangle, where this is 0.6 meters, and this is 1.5 meters long, because it allows me to solve for theta. That's why I find opposite hypotenuse, so sine of theta is 0.6 over 1.5 inverse sine, and I get theta is 24 degrees. This is kind of that key step here, because you can't really move forward until you solve for theta. So you have to use the length measurements to get that theta. Now it's not bad. I can go back to my diagram. I know theta. I know g. I can solve for h using opposite adjacent, so tangent. So I can now say tangent of theta is f of h all over f of g. 24. I don't know what f of h is. I want it. 196. And it's 87.3. Beautiful. Any questions? You can do a statement if you want there for horizontal force required. Is 87.3 newtons. And it's horizontal. There is no directionality. It's just east or west in this case if it was opposite. Beautiful. It's about looking for where are those forces. And if you can't come up with a force and you know the object isn't moving, make up a force that at least makes a triangle that, or the vectors aligned tip to tail. Right? So I know you understand that these should all cancel out. Question number 6 is our very last one, and it's my favorite one. I love this kind of question. Like, love it. Look at those beautiful hearts. That's true love. So, and if you don't have this, oh, it's sad. In an attempt to raise awareness for the Math Learning Center, the math department decides to hang a 10-kilogram sign above a door. Okay. The sign is going to be supported by a horizontal brace attached to a wire, a horizontal steel brace, and a wire attached to the wall. So here is I start with the wall. Now, my sign, here's my math sign, right? Woo, math. Okay. And I have this being attached, and it doesn't matter where you attach it, but it's attached to the wall. Okay? And it tells me that at the wall, it has a degree of 35 degrees. Now, I know it has a force going down, gravitational force. Again, I need to convert that, so maybe that'll be the first thing that I do. 10 kilograms multiplied by 9.8 gives me 98 newtons. Okay, so I have a 98 Newton force going down, and I have to figure out my 2 other measurements in terms of tension. This is the hardest part. There's a compression force and a tension force. Where's the tension in the wire going? Towards the wall? Beautiful. I can see you motioning with your hands. So here is my tension. That's my F of T, my tension. There's another force here. It's called a compression force. Okay. And it goes from the wall towards the mat. What, if you can't remember this part here, just remember it's going the opposite direction of the tension. The same thing, the beautiful mat sign is not going anywhere, so we arrange it to be F of G plus my compression force goes towards my tension. And what do you notice is that you have your gravitational force perpendicular to my compression, which makes it a 90-degree angle.
How picky are you about the arrows on top of it?
What do you mean by picky?
Like, just like,
Whether they should be there or whether they look the same?
no, like, English communication.
You should have them. So kind of if I have a vector, you can either have a vector like that, you could have a vector with an arrow like this, but you should have it. Because if it's just F, it's a force and it's not indicated as a vector. So it doesn't matter the type of arrow. I personally like the half arrow, but it's up to you what you prefer to look for. First thing I want to do is I want to solve for my, what does it want? Find the tension in the wire and the compression. Okay, great. In my picture that I have there, I have an interior angle, right? We said this was 35 degrees. It's still 35 degrees in this picture, and it's perfect. If I'm looking for F of C, opposite, and I know adjacent, so tangent of 35 is my compression force over my gravitational force. Biggest thing, please make sure your calculators are in degrees or you will get all of these questions incorrectly. You'll still get marks though. 68.6 newtons. And then I do the same thing to find my tension. I encourage you to use F of G instead of F of C in case you've made a mistake. So adjacent to hypotenuse, cosine. Adjacent is 98 over F of T divided by the cos of 35. 19.6 newtons. And that's it. And because it is a word problem, I would ask that you just write a statement. Therefore, tension in the wire is 119.6 newtons, and compression in the brace is 68.6 newtons. These don't have a directionality, they're just absolute values. They're magnitudes, right? Magnitudes of F of C, magnitudes of F of tension. And you're golden. That's it. You can see your homework. The worksheet is just really a part from your textbook, so questions number 1, 3 through 10, but the link is up on your Moodle page. Everyone in the class say bye.